come on. Let me see. All right, here we go. Is this not uploading again? Oh, it says the internet is not working. Okay, I'll deal with that later. Cool. Good morning. So, interestingly, I think I'm going crazy because you guys are now learning today what we did yesterday with 101. Oh, it's just driving me nuts. So hopefully I'll retain my sanity, but we'll see. No guarantees. So let's see, by the way, how your poll is doing. Where are we? 111 poll. Okay, so it's pretty strongly put in thingy. What about Avogadro's number? Oh yes, we are dealing with yeah. That's what stuff we are doing today. Okay, so it does look like multiple choice is the winner. I will technically keep this poll open until Friday. So, like, if anybody changes their mind or hasn't voted or whatever, it'll be there, so you guys can do that. Oh, well, Tyler, I mean, honestly, you will be okay if you just watch 101's video yesterday and then their video today. You'll have all the stuff we're doing today, so you're already halfway there. Okay. In Discord, there is a poll for how you guys want to no. So, like, if you had a free response, like a free response exam, I would still grade that, for sure. Yes, Shane. It would be as if you were giving me a Scantron for that. For open, yeah, I would have to, like, go through them all and grade them individually. Which is okay, that's fine, but you would not grade your own for that. So in Discord, Karen, if you go ahead and potentially, yes, Shane. Partial credit for that. So if you go to the, actually, let's see, if I had trouble, I couldn't do it this morning with oh, what do you know, I can do it. Okay, cool. So just throwing this massive Discord blob right here. Well, whatever, you guys don't need to see me for this part. If you go to your Chem C111 little area here, I don't even know where I am, something like this, somewhere over here. There we go. If you scroll down, you'll see a polls channel. You do that, you will click the either the squid or the vomiting muffin, rainbow vomiting muffin, depending on which vote you want to do. So if you want a multiple choice exam, you'll vote with this one, the vomiting muffin. If you want a pre-response exam, you will vote with the squid. Okay, so that is there, so you guys can do that. Okay, probably be an hour or an hour 15, depending. And it would be the number of questions that I would deem fitting for that amount of time. Unfortunately, no, Karen. We're definitely going to have naming on that, and I think... just let me find your syllabus, because I don't remember what I have written for you guys. Syllabus, here it is. Let's download it. Okay, let's see. So it'll be on 1 through 3, which will be stuff we are covering this week. So it will include stuff from this week. Okay? So let's get rid of that. Actually, let me just hide it entirely. Okay, cool. That wasn't the goal of that, so. So, yes. Okay, cool. So, with that, let us go. So, just to give you a rough number, Tyler, usually about 30 questions is appropriate for an exam one given about 75 minutes. So, that's about where it is. Keep in mind, some of this stuff is going to be like classify this cookie as a mixture or, something. Some of these will be pretty easy, right? So typically what I'll do is I will take the exam myself first, and I will give you 3 times as much time as it took me to do it. So that's actually a pretty standard thing for most instructors for exam writing. So that'll be about how long it would be. Okay. However, if it does look like a lot of people are having issues with time or whatever, we can look at that for other things. And as always, Kevin has the right answer. So there you go. Okay, cool. So last time we talked about balancing reactions and a couple of different types of reactions. So there is plenty of practice on Canvas for you guys on that. I'll probably give you more homework today because you guys love homework. And I love grading. Said no one ever. But gotta prepare you for your test, right? So, okay, cool. Anyways, now we're going to talk about, basically we're going to be taking stuff from the atomic level that we've talked about and bringing it into real life. So, we're going to see that a few years ago, relatively speaking, scientists came together and said, we are going to standardize a number of carbon-12 atoms such that the mass of all the atoms would equal 12 grams. Exactly 12 grams, right? So they decided we are going to standardize a particular number such that that number of carbon-12 atoms, a specific isotope, will be exactly 12 grams. And that number turned out to be what is abbreviated N sub A, which is 6.022 times 10 to the 23rd. So this is known as Avogadro's number. I guess I should be respectful and give him a capital A. But it turns out that this particular number, which does have relations in other aspects of chemistry, it turns out that that many atoms of carbon-12 will equal to exactly 12 grams. So 12 grams is not exactly a huge quantity. So consider that a teaspoon of water is 15 grams. So if you have some idea of how much a teaspoon of water would weigh, imagine instead you had carbon atoms instead of water molecules, and you would see that it is 6.022 times 10 to the 23rd atoms of carbon would weigh that much. So again, kind of showing us that atoms are really, 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 really small, absolutely tiny, tiny, tiny things. And we're understanding that we're going to be able to use this number to figure out how to bring things from atom level into real life quantities. So, this number is also known as 1 mole. And before we go crazy towards that, how many eggs are in a dozen? And now let's say how many are in 3.5 dozen? I have to do the math too. 6 plus 36, 42 eggs, right? We could technically do this using a conversion factor, right? We could say 3.5 dozen times 12 eggs per 1 dozen, and poof, there we go, 42 eggs. So, note, again, this is just a conversion factor, one that we all presumably know. We're going to see the same thing is going to apply here. And while this number in itself is kind of more used for bizarre theoretical calculations, we're going to see we have one more component to that conversion factor that is going to be very important for us. We're going to see that what the scientists decided before, 6.022 times 10 to the 23rd carbon-12 atoms, which we can just verbally say 1 mole of carbon-12 atoms, is going to be 12 grams of carbon-12. And so this is kind of a standard. And from that, we're able to expand and say 1 mole of any atom is going to be equal to the atomic mass in grams. So because all of these were carbon-12s, that's one isotope, we're going to say it's exactly 12, and that's our definition. However, we remember learning that most elements do have multiple isotopes, right? Like we saw that bromine had those 2 isotopes, and I don't know, platinum is 8 or whatever, you know. And we were able to see that a statistical average of all of those isotopes gave us the atomic mass, right? And that told us, you know, on average, you know, if we were to pick a hydrogen atom, you know, out of a whole bunch of hydrogen atoms, it would, on average, each one would have 1.008 atomic mass units, right? We learned that about atomic mass. And we're going to see that this is going to be a very important conversion factor for us. We're going to see, for example, that 1 mole of hydrogen atoms is going to be 1.008 grams of hydrogen, or 1 mole of oxygen atoms is 16 grams of oxygen, or 1 mole of carbon atoms is 12.01 grams of carbon. Note, this is carbon with all its isotopes. If it were just carbon-12, it would be 12 exactly, but that's just a standard. It's very hard for us to get exact isotopes of things, so we're in this class just going to be dealing with atomic masses. And same thing here, 1 mole of, I don't know, gold atoms, gold, is going to be 195.7, I think it is, grams of gold. And so, we're going to be able to use this information to come up with a whole bunch of stuff that will drive you all crazy. And tomorrow, remember we are going to have a little bit tomorrow, we're going to talk about how we can apply this stuff into chemical reactions. But for right now, we're going to keep it simple and just talk about like individual compounds, individual atoms and stuff. And so, understanding that, remembering that 1 mole of anything is Avogadro's number of whatever the units happen to be. So 1 mole of atoms is Avogadro's number of atoms. 1 mole of molecules is Avogadro's number of molecules. 1 mole of eggs is 6.022 times 10 to the 23rd eggs. 1 mole of chemistry textbooks is Avogadro's number of chemistry textbooks. So we're going to see that from this, we're going to be able to get 3 conversion factors. So we saw, for example, 1 mole of gold atoms was equal to the atomic mass of gold. We could also say that 6.022 times 10 to the 23rd gold atoms would also be equal to that atomic mass in grams of gold. And using that, we can figure out some party trivia, I guess. So we could see that I have, let's say, a 50 gram, let's see, what's our favorite element? How about silver? We can see how many atoms that's going to be by understanding. Let me bust out my periodic table here. Oh no, I did not want to close this book. Oh well. Busting out this periodic table, we see silver is 10. Where did it go? 7.8682 grams of silver is equal to 1 mole silver, which is equal to silver atoms. And so, we're just going to use this like any other conversion factor. So we'll start with our measured quantity, which is 50 grams. And we're going to want to put grams on the bottom, so that's going to be our atomic mass. And we know that that is equal to Avogadro's number of atoms. In doing that, let's see. I'm sure Kevin has already done this, but let's see what we can do. Times 6.2 is going to be 2.79 times 10 to the 23rd. Awesome. And that's going to be atoms of silver, right? So we can see that, you know, whatever this particular sample happened to be, I'm just going to make this a little bit neater. We're able to calculate the number of atoms that were in there. Always, same things always apply here. But chances are it's going to just be from our measured quantity. So we see that this atomic mass of silver has, what, like 7 sig figs or something? Typically, you'll just want to use your measured quantity because your atomic mass will have way more sig figs than your starting number. But yes, you would technically still apply them. Yeah, because 50 has 3, so we're gonna keep 3 sig figs for the end. Okay. Other questions on that one? So let's see, what's the mass of a helium atom? We can do that. Starting with 1 atom. For this, I mean, presumably the sig figs are infinite because someone has counted 1 atom, but who the hell cares? It's 1 atom, like, forget it. Let's not worry about sig figs for this particular one because it's one atom. This is a totally theoretical calculation. We would never actually use this in real life, but we can do it. We're going to see that if we look at the periodic table, that we're going to get 4.003 is our atomic mass. So that one's going to go on top. We're going to put Avogadro's number on the bottom. Notice, as always, that atoms cancel out, right? I should have done this before. Grams cancel out. We're left with atoms on the top. This time, atoms are canceling out, so we're going to be left with grams. So, to the calculator I go. 4.003 divided by 6.022 times 10 to the 23rd. And I'm just going to do 4 sig figs because why not? Again, I would not worry about sig figs for this particular one because this is just a party trivia question. Yeah, or if you were to do 3 sig figs instead, it would exactly be 6.65 times 10 to the negative 24 grams. So super duper duper small, right? Tiny, tiny, tiny. It's kind of useless for us to talk about individual atoms because they're so damn small. Right? It's really like impossible to isolate one atom and to try and do anything with it. So we'll see how that's going to work. So on average, each helium atom weighs that many grams. Yeah, go ahead. It's from neutrons. Yeah, that'd be okay, Tyler. Especially since you guys have chosen multiple choice, like, it should be obvious. Like, a slight number like that would not be a problem. So, Shane, to answer your question, the extra mass is always from neutrons. So remember that except for one particular isotope, every atom has either equal to or more neutrons than protons. So, yeah. And electrons, remember, don't really add anything. They're tiny, so we kind of ignore them. Cool. Awesome. Okay. All right, so we're done with party trivia. So, again, this sort of thing you would use to amaze your friends, but not much practical use here. However, we're going to see that moles are going to be a much better way, much more useful quantity for us to deal with. We've talked about atoms here. We can talk about molecules as well, or compounds. We can go ahead and understand that if we take a look at water, for example, we know that one water molecule is going to be 2 atoms of hydrogen plus 1 atom of oxygen, right? And so, because of this, we're going to be able to figure out what is called the molar mass of water, which will be 2 times the atomic mass of hydrogen plus 1 times the atomic mass of oxygen, which is going to be 2 times 1.008 plus 1 times 16. Again, I just have these numbers memorized because I'm a nerd. Or whenever you do this, you'll get 18.016. Or if you were to, again, sig figs, you might round this to 18.02. Does not really matter. Exactly. And so that's going to tell us that 1 mole of water molecules would be about 18.02 grams. So again, while you're friends, you go say, look, I have a tablespoon of water, which is about 15 grams or so. Again, not very much. You would be able to say, hey, this is 6.022 times 10 to the 23rd molecules of water. And so for any compound, we can do this. Again, this was called the molar mass, which is the mass of 1 mole. We can do the same for a whole bunch of compounds. So let's go ahead and test your skills. Let's see, how about we do dinitrogen pentoxide. So don't forget, we do have naming on our exam, so let's just do a quick review, right? Why not? I want you guys to calculate for me the molar masses of these two. Well, I yawn and stretch. So of course, you're going to need to be able to decipher what these names mean, right? So that'll be kind of the first step, and then after that, you're going to have to add all their atomic masses together. So, fine, we'll do the first one together. Remember, carbonate is CO3 2-, sodium Na+. Charge balance them, you get Na2CO3. Kevin, I think you've done something a little bit incorrect there. Because that is almost twice what we should get. So, if we do that, we're going to add 2 sodiums plus 1 carbon. I'll make this parentheses really obvious. Plus 3 oxygens, which is going to be 2 times 22.99 plus 12.01 plus 3 times 16. And I've run out of room, as always. I'll just do it on this side. This should be like 106.99 or something, or like 107. I think something went wrong with your calculation. There we go. Yeah. So, perfect. So I don't know what you did the first time. Maybe just an accidental multiply by 2 somewhere. So, cool. Units of molar mass are grams per mole usually, because we understand that as a conversion factor, it's 1 mole of whatever, sodium carbonate in this case, is equal to 105.99 grams. Okay, and again, I would not worry about sig figs for this because, again, this is theoretical stuff. So we don't have to worry about sig figs here. Does anybody have any questions on that one? Alright. So next one, hopefully the naming is easier. Non-metal, right? Things are easier for us. What's the formula of that guy? The creature is snoring. I don't know if you guys can hear him. Starler's already done it for us. Okay, so yes, the formula is N2O5, right? Thankfully, dinitrogen pentoxide, easy for us. So we're going to add 2 times nitrogen plus 5 times oxygen, which is 2 times 14.01 plus 5 times 16, which apparently is 108. I'm going to just say 0.01 because whatever, I don't care. Grams per mole. Okay, so calculating molar mass, hopefully not a crazy skill. Should be a fairly easy one. We're just adding up the atomic masses of everything in the compound. Let's do one more. Sodium chloride. Oh, I even gave you the formula. Shame on me. Oh well, too late now. The molar mass will be equal to the mass of sodium plus the mass of chloride, or chlorine rather, which is 22.99 plus 35.45. Again, these numbers are for the periodic table, just in case anybody's forgotten. And yes, so we're going to get, in this case, 58.44 grams per mole. Hooray! Okay. I think you guys are pretty sick of doing that. There are a lot of things we can do with this. We're going to use it as a conversion factor, of course, so that'll be able to get us between grams and moles. But we can also do other stuff. We can find, for example, the let's use this molar mass. Let's use them as a conversion factor. How about we have what's the like? Of course you will. Yay! I'll try and upload that today for you guys. Because we love math and homework. Ugh. You guys are killing me. Okay. Let's use this number. Let's say we have, I don't know, what's the the daily, Christmas cube. What's the amount of sodium that we want daily? I guess this doesn't matter because it's sodium chloride. Whatever. Okay, let's say we have 22.94 grams. Okay, let's do these two. The second one, a little bit trickier. First one, we'll just use the conversion factor like any other conversion factor. Which will just give us apparently 0.39. Come on, give me more sig figs than that, Star-Lord. You can do it. I gave you 4 sig figs for our grams. Give me 4 sig figs for our moles. Do it, do it. What are the numbers? I don't want to calculate this stuff. You guys are doing it. And while you guys are doing that, is that for the second one, Star-Lord? Okay. For the first one, for the sodium chloride, give me the number with 4 sig figs. So we have some interesting things here. Okay, well, let me let's first do this part. What was it? 11. What was our molar mass? 108, 101. Okay. Oops. Oh no. It might not be. I think you probably are right with that one. I think you're okay with that. Because in this question I'm asking for moles of nitrogen. This one that we've written out here would give us moles of dinitrogen pentoxide. So yes, you're totally, I think you're right on with the So it looks like we have some just general confusion. If we were to do this, I think your 0.638 I guess, is moles of N2O5, right? Which part is confusing? So one thing, yeah, that was the problem. We're just converting the 22.94 grams into moles. We're just converting them, that's it. Yeah, we're just trying to figure out what these are. Alrighty, so Kevin, just so you know, the moles does not mean just times 10 to the 23rd. So that would not be correct there. If you were to multiply that number of moles by Avogadro's number, you could find the number of molecules of N2O5. But you can't just chuck on the times 10 to the 23rd. Okay. And now let's go ahead and look at this problem. So this problem, I'm asking for moles of nitrogen itself. However, we have calculated moles of dinitrogen pentoxide. So how on earth are we going to have some sort of conversion factor that will be able to tell us how many moles of nitrogen is going to be in the moles of N2O5? How are we going to figure out what this is going to be? Well, we know for every one molecule of N2O5, we have 2 nitrogens, right? If we had a dozen dinitrogen pentoxides, we would have 24 nitrogens. So this is going to tell us that we have 2 moles of nitrogen for every 1 mole of this particular compound. And so, since we have, I'm going to just do this in a different color because I think this is just going to already confuse the crap out of you. So, perhaps I was overly hasty in giving you this problem to start, but that's okay. We'll survive. With this, what we're going to want to do is use the correct numbers to convert between the compound and this particular atom, since that's what I've asked for in this problem. And I think, Starlord, you had the right number. I think that is going to be your 11.79, I'm sorry, 1.179 moles of nitrogen. That number looks right to me. It's about twice. Actually, it's a little bit too small. Forget it. Your number is wrong. I think. Do the math for me, someone. Where's Oz? He's dying. You have a little hairball little dude. You want to say hi? Here he is. Yay! And he's got his little bumblebee outfit. Great. Perfect. Awesome. So, does that make a little bit of sense? I understand that this was, I think, in my opinion, it was I went too fast. I gave you this when we weren't quite set on the previous step, so I apologize for that. But if you guys have any questions on this one, we'll go back and do a couple more easier ones, but that don't have these extra steps. But are there any that have? So for 0? Oh, for oxygen. Yeah. Absolutely. Shane, that would be absolutely correct. If I wanted moles of oxygen, you would do 5 moles oxygen divided by 1 mole of N2O5. Okay. Cool. So, off you go, Oz. Yeah, I think that's the thing is because I think I misled you into thinking it was harder than it was, and so I apologize for that. So let us step back a little bit. Okay, how about we do? We'll do just one more. How about I don't know. No, I don't think so. This is the first time we've talked about moles in this class. But we have talked about chemical formulas and understanding like the ratio that we had here. Like this part should be familiar, hopefully. Like just understanding we have 2 nitrogens in that compound. Okay. Well, if you want, in 101, I did this topic yesterday for them, and I'm sure I went in more detail with them because it's a lower level, so we're going to, they go a little bit slower. That seems really high. That leads me to believe it's not quite correct. What was your molar mass, Starlord? These are just unit conversions. So in order to do this conversion, we have to figure out the molar mass first, which is going to be our conversion factor. Okay, well, so look at this. So this formula, this means 6 carbons, 12 hydrogens, 6 oxygens, right? So that's how we understand how many of an atom are within a particular compound, right? Yep. Yeah, between mass and moles. And so if you were to do all this stuff, the molar mass is 6 times 12.01 plus 12 times 1.008 plus 6 times 16, which is roughly 180.2. I just happen to know that. Again, you guys would do the math, but should be about 180.2. And so we would take our 28.6 grams and use that number that we got to convert it into moles. And it looks like people are getting 0.159. For their moles of glucose or whatever this happens to be. Correct. Yeah. Because this is a conversion factor, it tells us 180.2 grams is equal to 1 moles. Yeah, I know, there's a lot of numbers, and there's going to be more numbers today. Yeah, exactly, Shane. Absolutely. So if I wanted moles of carbon from that, I could, you would multiply it by 6. Because this number, this 0.159, is moles of glucose molecules. And each glucose molecule is made of those 24 different atoms, right? So we have 6 carbons, 6 things. Double check, Kevin, because I'm pretty sure this one should be... I mean, even 6 times 12 is 48. No, is 72. 6 times 6... No, 6 times 12. What is 6 times 12? Math is hard, guys. Yeah, 72, right? And then 6 times 16 is what, 96? So that already is going to be way more than 108. So, double check. I understand lots of this math. It's easy to mess a button up on the calculator and that'll throw it off. So, okay. You guys want to know what the point of doing all this stuff was? I hope so too. What we can do, there's a number of things we can do with molar mass. So yes, we can use it as a conversion factor to go between mass and moles. Yes, we could do that, Shane. It's also going to cover the other two things we're going to go over right now. So there will be kind of more uses for this molar mass than we've just used right there. Okay, so other use number 1 is finding percent composition. That is going to be another use of the molar mass. For example, if I wanted to see what is the percent of sodium in sodium chloride, as in, like if we have a given mass of sodium chloride, how much of that is actually sodium, how much of it is actually chlorine? We could find that out by understanding that the percent of an element is the mass of that element over the mass of the compound. And very often, this is going to be the molar mass for both of them. $395, 39%. Okay, I see what you're saying. Yeah. Okay, I was going to say 395 is really high. So, if we were to find the percent of sodium, we would say it's sodium over sodium chloride, right? Which is going to be 22.99 over 58.44. This is the molar mass of sodium chloride. We'd already calculated that, which Karen has already done for us. And again, because this is a percent, we're going to have that. Again, sig figs are not going to really be a problem here because this is, again, theoretical stuff. We don't have measured quantities here. All right, and that's going to tell us, by the way, that we have 60.7% chlorine, right? Because sodium chloride is only made of two things, so if one thing is 39%, the other thing is going to be the 60%, right? Because it should add up to 100. And from this, we can say of a 5-gram sample of sodium chloride, we can see how many grams of sodium there are by using this percentage that we just figured out. Since we know that this was 39%, correct, this is by mass. So Shane, the one that you did, the 50-50, is actually going to be what's called the mole fraction. That's something we'll cover next chapter, maybe, or maybe it's in the gas chapter, I don't remember. But that's a different thing. So yeah, this is percent by mass. All right, and that's going to be 1.95 grams. So the point of this is, if you are a hypertensive individual or have a hypertensive patient or whatever, and they need to know, okay, how much salt can they put on their food if they have to be watching their sodium, right? So understanding that sodium is 39% of sodium chloride, we can say, okay, this 5 grams of salt is going to give you just under 2 grams of sodium. So if you're watching your individual sodium, this can be one way that you could figure it out. Of course, you could just look on the nutrition facts or whatever, but if you're cooking or something and the recipe says 5 grams of salt, you could use this to figure out a more exact number of how much sodium you have in there. Okay, so that's another use of this. We can do another problem. How about we do the percent of nitrogen in that compound that we had earlier? Let's use blue now because I like different things. So that's going to say the percent of nitrogen. Notice now, because we have 2 nitrogens in this compound, we have to take account of that, because 1 nitrogen would be whatever it's going to be, but we have 2 nitrogens in here. And so we have to take account for that. So that's going to be 2 nitrogens over, so the entire mass, which was, anybody remember? Where the heck is this? 108.01. Grams are going to just cancel out, so we'll get that out of there. So remember, we need 2 of these numbers, so that's going to be 28 over 108, which is going to be equal to, I'm going to say 26 would make more sense. Ah, you did N2O. Got it. Okay. Yeah. No worries. Okay, so about 25.9. Not going to really worry about the rounding here. Again, this is a theoretical thing. Alrighty, so we can do this for anything, right? We can figure out the mass or the percentage of a particular element in a compound using this formula. So we have the mass of all the nitrogens over the mass of the whole thing. That's going to give us the percentage. Okay, and we could use that percentage if we wanted in further calculations. But in the interest of time, I am going to have to move on. So again, we can touch on this tomorrow. But we have one more thing to cover, and I want to do that before we end. Alrighty, so that being said, we can go the opposite way. We can also figure out how to get a formula from percentages. And in this case, so we saw that the sodium chloride was 39% sodium and therefore 60.9% chlorine, right, given to us in this case. What we're going to be able to see is we're going to want to convert these numbers into moles so that we can see how many of each atom we have in a particular sample. One thing we kind of always want to do is just assume 100 grams of your, it was 39.3? Okay, that's fine. I'll fix them. 60.7 then. Okay, cool. If we assume 100 gram sample, that's going to tell us that we have 39.3 grams of sodium. And therefore 60.7 grams of chlorine. And just to make sure we're not violating anything, very clearly we can see if we put all this stuff together, we should get still 39.3% sodium and 60.7% chlorine. So we're not breaking any rules. You can assume whatever mass you want, as long as the percentages are correct. But 100 is easiest because it's a percent. Hundreds make sense for us. However, this does not tell us, this alone doesn't tell us how many of each atom. The way to check your work here, yeah, you can, once you find out your formula, you can go back and do the percentages and they should be the same. That would be one way to check it. So what we're going to want to do is convert both of these into moles using their respective atomic masses. And if we do this, 39.3 divided by 22.99, we're going to get 1.71 moles. And 60.7 divided by 45, miraculously, is 1.71 moles of chlorine. All right, and remembering that moles, just like dozens, it's saying, you know, we have 1.71 dozen sodiums for every 1.71 dozen chlorines, right? It's just another word like that. So this tells us they're the same, right? We have a ratio of 1.71 to 1.71, which means it's a 1-to-1 ratio. And so we have 1 sodium for every chlorine. And so yeah, this is totally checking our work from before. You can take those percentages, put them back in, and make sure you get the same compound out. Or now you can take this compound and find the percentages, and they should be the same from before as well. Alrighty, I have an example here. These ones, it's hard to, I can't just make up examples like I like to normally, because if I don't get it exactly right, it'll just mess up. So let me do one example for you guys. And then we'll do one more example tomorrow, I think. Okay, So, yep, no, I would not use Avogadro. We're just looking for a formula. So remember, moles also tells us the number of atoms. It's just a lot easier of a number to work with. So yes, if you wanted to find the exact number of atoms, we could totally use Avogadro's number, but it's a pain in the ass. Why would you do that? Like, I mean, keeping it as moles is a lot easier. But you could totally, if you are in love with Avogadro's number, go right ahead, use it all you like, but not necessary here. Okay, we are going to run a little bit late today, but it's a good thing. 24.2% sulfur and 48.2% oxygen. So let's say we have these ratios. So we've got them from some experiment or something. Someone has burned a lot of stuff and figured out that there's this percentage of each element in a particular compound. So first step, just like before, we're going to assume we have 100 grams. And so we'll just be able to convert these percentages into grams. No problem, you can always do that. Since again, grams do not give us the information, we're going to want to convert them into something that we can compare. And so that's going to be moles, or if you are insane like Shane, you could convert them into atoms instead. Totally okay. But yeah, Shane is absurd. So we're going to go to our periodic table and get our atomic masses. Thankfully, I have done this one already, so I have the numbers for us. I totally know I'm going super fast here, but that's just because we're out of time. So remember, you can always like pause the videos and stuff and let it absorb, and then you can go. You can also do that with a live video. You can totally just pause it in the middle and just it'll pick up where you left off. Alrighty, so for this one, it's not as obvious to us. So we have a ratio of 0.503 to 0.754 to 0.3.01. Not so obvious for us, right? We cannot see, like last time they were the same number, right? This time it's a little bit more complicated. So in a situation like this, what we're going to want to do is divide by the smallest number. And so if we do that, we get 0.503. We're going to divide them all by 0.503. If we do that, these are the numbers we get out. And so this ratio is a little bit easier to see. We have a ratio of 1 to 1.5 to 6. And so that would technically mean we had, remember we had manganese, sulfur, and oxygen. So technically that would be manganese S 1.506. But do we ever write formulas like that? Nope. So let's go ahead and adjust to make these integers. Yeah, so like Kevin has noticed that this is exactly the same thing is saying, okay, we have something that's 1.5, so we're going to multiply all of this by 2. And by doing so, if we multiply this by 2, that's a 2 to 3 to 12 ratio. So you want to kind of look at your numbers and think, okay, is there any... Calm down, Cotton. Is there any way we can make all of these numbers have integers? And so looking at that, if you had a 1-to-1, let's just look at those two. If you wanted to make these two numbers be integers, and while keeping the ratio the same, you would just multiply by 2. That's the same as a 2 to 3 ratio. A 1 to 1.5 is the same as a 2 to 3. And so, I will give you a handy guide here. If in your thing you have 0.5, multiply by 2. Something with 0.5. So it could be 1.5, 2.5, 6.5, whatever it is. If there's a 0.5 in there, multiply everything by 2. If you have 0.33, we're going to see that all of these will be things we can multiply if we see these particular decimals in our numbers. So if we look at our ratios and they have these weird decimals in them, try multiplying by one of these guys based on what your decimal is. And that should hopefully get rid of all of those decimals and leave you with happy integers. And it goes the same way up to 4, up to 5, let's say. You don't really want to round it. You can't say, okay, well, 1.5 should round up to 2. No, don't do that. If it's very close, like if it's like 3.99 or something, go ahead or round it to 4. That's fine. It's close enough. But if it's like 3.33, don't round that. Okay, so if it's super, super close, like within 0.05 or something, fine, round it. But other than that, try multiplying by one of these guys, and that'll get rid of your decimals for you. Okay, so we will do another one of these tomorrow. I just want to let you guys absorb this and go and cry in the shower or whatever, whatever makes you happy. There will be homework on this Help Us later today, so you guys can practice. How the homework is going to work, so you'll submit it on Sunday like usual. At midnight on Monday, as in like what? Yes, it will. 1 minute past that due date for the homework, I'll have the key available for you guys so you can check your homework. So when you wake up, or if you're still up at midnight, you can just check your answers right away and see to make sure that you're understanding it correctly. Because if it is a multiple choice question, you'll be able to take multiple choice exam rather. You'll be able to take that exam at any point on Monday. So you should be able to have enough time to look at your stuff, your answers, and then take the exam after. Okay? So don't forget, I will be streaming tomorrow. We have a little bit more left to do in Chapter 3. The last couple sections. Yeah, Karen, that would be correct. So, Sunday at 11:59, you turn in your homework. 1 minute later, poof, the keys are there. Oh, okay. I understand we've done a lot of math today. It's a good question. Do I have a practice exam for this? Maybe. I'll look around and see if I have one. And if I do, I'll post it. But it's been a while since I've done 101, or 111, the equivalent. So it may be on like an old computer somewhere that I would have to find. So, but I'll look. I'll see if I can find one for you guys. Okay. So with that, see you guys tomorrow. Don't forget you still have naming homework to do. So hopefully you guys are still working on that. We're going to have this homework, which is going to also include chemical reactions. This is going to be a little bit of stuff as well for what we're going to cover tomorrow. Okay, so I will post that today, but you may not be able to do all of it until tomorrow. Okay? So, have fun. See you guys. Enjoy. Stay safe as always. I'll put the videos up, blah, blah, blah. Same as always. Okay, take care.